Okay, so we are going to do this last section of chapter 4, and some professors omit this because it involves complex numbers, but I think this is just too important not to do, because it really shows the what polynomials essentially are. Okay, and also we need to talk, if this is an algebra course, we need to talk about the fundamental theorem of algebra, which is in this chapter. Okay, so we've already looked at the polynomials with real zeros. Okay, so a real zero is just a number that if you plug it into a polynomial, you get 0. And so all of these polynomials over here have real zeros. In fact, all of their, they're going to have, their number of zeros that they have are actually equal to their degree. 2 is if you plug 2 into 3x minus 6, you get 0. Okay. Or if you set this equal to 0, you get x equals 2. And in fact, we can write this as 3 times x minus 2. X minus 2 will be a factor. If you set this equal to 0 and factor it, which is what we get over here, you'll see that the zeros are, well, this is x minus 0, so x minus 4, x plus 4. So the real zeros are 0, 4, and negative 4. For this one, 2x squared minus 14, if you factor out the 2, you'll get x2 times x squared minus 7. Set that equal to 0, you get x squared equals 7. So the two solutions would be plus or minus the square root of 7. And so in fact this factors this as 2 times x minus square root of 7 and x plus square root of 7. And then x squared plus x minus 1. This is a second degree polynomial. We can use the quadratic formula where a is 1, b is 1, c is negative 1. We plug them in and we get two real numbers, negative 1 plus square root 5 over 2, negative 1 minus square root 5 over 2. And that gives us the factors. So this fact indeed factors. It doesn't factor very nicely, but if you multiply this out, you'll see that things cancel and we in fact get x squared plus x minus 1. Notice all these factors are in the form of x minus a real 0. But there are some polynomials that don't have real zeros. Okay, x squared plus 1, x squared minus 2x plus 3, x squared plus 4x squared plus 5, and x to the fourth plus 9. And you can see that the first, second, third, and fourth, why they won't have any zeros, because x squared, x to the fourth, those are all going to be positive. Okay, so there's no real number that this can ever be 0, or this can be 0, or this can be 0. And if you use the quadratic formula for this second degree polynomial, you'll see that you'll be having a square root of a negative number. Okay, so none of these have real zeros, but we would still like to give them some sense of factorization and some sort of 0. So the question is, can we invent zeros for these polynomials? And the answer is yes, we can. We can invent them using complex numbers. And complex numbers, they have a lot of applications, not just in math, but also in physics and engineering. But what we're concerned is we like them because we can create solutions of these equations. But it turns out we can get by creating a special complex number, namely I, the square root of negative 1, we can use that's just enough to find to create all the zeros, or invent all the zeros for all possible polynomials. Now, we said over and over again, you can't take the square root of a negative number, and that's true if you're working in the real numbers. But now we're creating this imaginary number, the square root of negative 1, and we're just declaring it to be the square root of negative 1, so that I squared is equal to negative 1. Again, this is not real. Now, that by itself wouldn't be much useful, but we can create a whole bunch of other numbers based on this. And so we're talking about a complex number, and we're going to define a complex number to be an expression of the form a plus bi, where a and b are real numbers. Okay, so these are all examples of complex numbers. 3 plus 4i, Okay, in this case, A would be 3, B would be 4. Negative 7 minus I, in this case, A would be negative 7, and B would be negative 1, because we can write this as plus negative 1I. 2I, well, there's no real part, but we can see it as a 0, so we can write this as 0 plus 2I. So A is 0, and B is 2. And then finally, 6. 6 is going to be, we can write this as 6 plus 0I. So in this case, A is 6 and B is 0. And this shows you that every real number is also a complex number.